Hi, my name is Jeremy Adams, and I will be discussing E1 and E2 reactions today. To understand E1 reactions, it is important to understand carbocations and how they work. The stability of carbocations from greatest to least is as follows: tertiary, secondary, primary, and methyl. E1 reactions will produce carbocations in an intermediate step. And if a secondary carbocation is produced and there is a tertiary carbocation spot available, the molecule will go under a methyl shift or a hydrogen shift to move this positive charge to a more stable carbocation within the molecule. To understand E1 reactions, it's important to understand leaving groups. Halogens are great leaving groups, and the bigger the halogen, the better the leaving group. To better understand this, if you look at column 9 on the periodic table, the leaving groups from best to worst are as follows: iodine, bromine, chlorine, and fluorine. These atoms make great leaving groups because they only need one electron to fill their outermost ring. And so when they leave and they get donated that electron, they have a full octet, and they have the ability to spread out the negative charge over a larger area as you go down the column 9. So iodine can spread that negative charge over a lot more area than a fluorine can, and that's what makes it a better leaving group. E1 reactions. The rate of an E1 reaction is determined by K, which is a constant, times the concentration of the substrate. The concentration of the substrate matters in the rate of the reaction because if it has a bad leaving group, it's harder for the substrate to make a carbocation. If this is so, the rate of the reaction will be slowed. On the other hand, if there is a good leaving group, the substrate can form the carbocation a lot quicker, making the rate of the reaction a lot faster. The steps of an E1 reaction are as followed. The leaving group will leave to form the carbocation, and during this time, a methyl shift or a hydrogen shift can occur, but only if needed, to move the positive charge to a more stable carbocation location. Lone electron pairs of the nucleophile will snatch a hydrogen from the beta carbon, not the alpha carbon, and you'll see that later on. And after that happens, a double bond will form with the leftover electrons after the hydrogen is taken. E1 examples. Here we are reacting 2-methyl-3-bromopentane with methanol. In this reaction, we can see that bromine is the leaving group, and all the way to the left with the pink arrow, it leaves and forms a carbocation, which we notice is a secondary carbocation, which has a tertiary carbocation right next to it. And here we see the hydrogen move to the secondary carbocation, which is a hydrogen shift, which forms a tertiary carbocation on the neighboring carbon. Here we see the lone pairs of the oxygen reach out and grab the hydrogen, which forms a double bond, and we will get two products. We have a major product and a minor product. Here we can see that the double bond has formed between the tertiary and secondary carbon, but the less stable and minor product would be a double bond between the tertiary and methyl carbon. So our answer is the more stable double bond between the secondary and tertiary carbon. Here we are reacting 2-dimethyl-3-chloropentane with water. In this reaction, we can see that chlorine is a leaving group, so that is the first step. The chlorine leaves and creates a secondary carbocation. The neighboring carbon is a quaternary carbon, and if that methyl shifted, it would create a tertiary carbocation. So it does to gain greater stability and moves the positive charge to the tertiary carbocation with that methyl shift. After that methyl shift occurs, the water molecule, or the oxygen lone pair electrons, reach out and grab the hydrogen from the original secondary carbocation. This creates a double bond with the electrons that were holding the hydrogen together onto that carbon, creates a double bond between the two carbons. Here we can get a better look of the methyl shift that occurred in the previous slide. You see that the picture on the left represents the molecule after the chlorine has left and created the secondary carbocation with a quaternary carbon next to it. When this happens, the methyl will move and create a tertiary carbocation out of the secondary carbocation originally. Now, many will ask why the positive charge moves as well. Well, the secondary carbocation has a hydrogen that is not shown in this picture connected to it as well. And so when that methyl moves, that maxes out the number of bonds that that carbon can have. So that positive charge will always move to the donating either a hydrogen or a methyl carbon, creating a new carbocation. We will also get two products out of this reaction. We will get a major and minor product. The reason for the major product being the major is that it's double bonded between two tertiary carbons as opposed to a tertiary and a methyl carbon on the top. E2 reactions. The rate of an E2 reaction is dependent upon K, which is constant, times the concentration of the base times the concentration of the substrate. The following is the E2 reaction steps. All in one step, a leaving group will leave and a nucleophile will attack a hydrogen at the same time. There is no intermediate step in an E2 reaction, unlike E1 reactions. And as a result of this leaving group leaving and a nucleophile attacking the hydrogen at the same time, a double bond will form. In this E2 example, we will be going over the reaction between 2-methyl-3-bromobutane reacting with sodium methoxide and ethyl alcohol. In this reaction, the bromine leaves at the same time as those lone electrons following the blue and purple arrows reach out to those hydrogens. This is all one step, remember, there is no intermediate step. So if we follow the blue arrow, it reaches out and grabs the hydrogen off of the carbon to the left, which is a more substituted carbon. It is not a methyl carbon. And that will give us the Zaitsev orientation of the double bond. If we follow the purple arrow of the lone pair of electrons, which grab the hydrogen off of the methyl carbon at the end, which one carbon is not shown there, one hydrogen is not shown there. There should be a third hydrogen. But if the lone pair of electrons reach out and grab the purple hydrogen, we will get the Hoffman orientation of the double bond. In most cases, the Zaitsev orientation of the double bond is the more stable bond, which in this case it is because it is formed between a tertiary and a secondary carbon, unlike the less stable one, which is the double bond is between a secondary and a primary carbon. Comparing E1 to E2. The rate law of E1 is only based on the substrate, while the rate law of E2 reactions are based off the substrate and the base. The key step of E1 reactions is the formation of the carbocation, and E2 is the deprotonation of the substrate. The barrier of E1 reactions, which you must get across, is carbocation stability. It is very important of the stability of a carbocation for an E1 reaction to work. For E2 reactions, you have to consider stereochemistry and how big the molecules are surrounding the carbon that you want to attack with your nucleophile. And a great way to determine if E1 reactions are going to occur compared to E2 is by looking at the base. E1 reactions require a weak base, such as H2O or CH3OH. In E2 reactions, they require a strong base, such as NaOH, and that is a great way to determine if an E1 reaction or an E2 reaction is going to occur. Thank you for your time, and I hope you enjoyed the slideshow.